Okay, welcome to this final video of the course. So in this video we're going to look at some applications of the classification of simple compact Lie algebras to particle physics beyond the standard model. And before discussing these grand unified theories, I want to focus a bit on what one can learn starting from the Dynkin diagram of a compact simple Lie algebra about its subalgebras, or at least some special subalgebras of them. So here's a general question: how to find, for instance, non-simple Lie algebras as subalgebras of a compact simple Lie algebra. Lie algebra, say G. Starting from its Dynkin diagram. So here's one way. And now this way goes by, in quotation marks, dropping a node in the Dynkin diagram. So what do I mean by this? So let's consider a general Dynkin diagram of G of the following form. So it has some node here, and perhaps it has two neighboring single lines, and then arbitrary large parts of the diagram on the left and right side. And let's say that this particular node corresponds to the rth simple root of G. So if G is of rank R, so rank R, then, well, what does this mean in terms of the roots? So we have some vector alpha r in the r-dimensional space, and then there will be other roots, alpha 1, alpha 2, say up to alpha r minus 1, and by definition these simple roots, they span this r-dimensional space. Now this means in particular that if I leave out this last simple root alpha r, that the other roots, they span up a hyperplane in this r-dimensional space. So it's an r minus 1 dimensional hyperplane. So let's say it looks something like this. So this is a r minus 1 dimensional hyperplane. So what we can do is then, since we only really care about the inner products, so the relative lengths and the angles between these roots, if I want to specify the actual Lie algebra, or choose a basis for the Lie algebra, I have to choose a basis of Cartan generators, right? They determine a basis of this r-dimensional space, and I'm free to choose whatever basis I like. Suppose a orthogonal basis. So what I can do is I can choose my Cartan generators such that the first r minus 1 of them, they span this r minus 1 dimensional space, and then there is a last one, say h r, whose eigenvalues correspond to the direction perpendicular to this space. Right, so what I'm saying is that one may choose the Cartan generators such that acting with Hj on, no, let's say Hr, on the generators corresponding to the first r-1 roots. So E alpha hat j vanishes for j from 1 up to r-1. Right, because what is this? This is exactly, no, this has an eigenvalue. This is an eigenvector of the Cartan generators with eigenvalue, the rth component of this this root. So this is saying that we're going to take alpha jr to be 0 for j from 1 up to r-1. Okay, so what does that mean? So then, if I look at these Cartan generators, so h1 up to hr, together with all the possible roots that I can get from these r-1 simple roots by Wall reflections. So all the roots I'll get from those are simply all the roots of G that lie in this plane. So together with E alpha, where the root alpha is a linear combination of alpha 1 up to alpha -1. So this spans a subalgebra. Sorry, r-1. And not just a subalgebra, it's also a compact subalgebra. Compact subalgebra. Let's call that G prime with G. Whose Dynkin diagram is simply the one that I had before, but then dropping this node. Dynkin diagram of this form. Okay. So why is this really a subalgebra? So the only thing I have to check is that the commutators of these generators are in the subalgebra again. But that is immediately clear because these generators corresponding to the roots, they are eigenvectors in the adjoint representation of the Cartan generator, so their commutator is just proportional to E of alpha itself. Well, the commutators of the Cartan generators with themselves, they vanish, so they're also trivially in G prime. So the only thing really one should check is that if you take two roots in this linear subspace, take their commutator, well, that should correspond to, well, either it vanishes or it corresponds to another generator corresponding to a root that is the sum of the first two roots. But the sum of two roots should again be in this linear subspace. So it is really included in G prime. So here we found a compact subalgebra, which is not necessarily simple, depending exactly on where I choose this node to drop. So in this case, it splits into two disconnected components. So this is a non-simple Lie algebra that is composed of two simple parts. But we can actually do it slightly better. We can increase this subalgebra a bit by noticing that if we include not just the first R-1 Cartan generators, but also the last one, together with the same set of roots that I had there, so in general, E of alpha, for which the rth component of the root is equal to 0. So this spans a subalgebra that I claim is of the form G prime plus an additional U1 Lie algebra. So remember, what is a U1 Lie algebra? So U1, the Lie group, it's an abelian Lie group. So that means, and it's one dimensional, so it has a single generator, which of course commutes with itself. So more generally, any one-dimensional Lie algebra is of the type U1. So why can we think of the span of these generators as G prime plus U1? Well, the U1 direction is simply spanned by this last Cartan generator. Because computing the commutator of H of R with any of the other generators actually vanishes. Because H of R with all the generators in G prime is actually 0. It's certainly 0 when I take the commutator with any Cartan generator by definition. But also if I take the commutator with one of these root generators, then because the rth component of the root vanishes, it is going to vanish. So in general, by dropping a root, we get a direct sum of two simple Lie algebras, and I can add to this another U1, which is technically speaking not a compact Lie algebra, but if I go to the Lie group, then this would correspond to a U1 Lie group, which is a compact Lie group. So how is this relevant in the light of grand unified theories? So let's move there. So remember that the standard model of particle physics is a gauge theory. So it has a local symmetry where the local symmetry group is a standard model gauge group. It's a gauge theory with gauge group SU3 for the strong nuclear force, and then SU2 cross U1, which together describe the electroweak part of the gauge theory. So what does it mean for this to be the gauge group? It means that there are gauge bosons that transform under the adjoint representation of this group. So with gauge bosons, so really the force carriers transforming in the adjoint representation of this gauge group. So now, since we understand that the dimensionality of the adjoint representation is just a dimension of the Lie group, we can now understand how many gauge bosons there are. So for SU3, that is an 8-dimensional Lie group, so there must be 8 gauge bosons. So these are the 8 gluons. Then SU2 is 3-dimensional, so there are the 3 vector bosons, if you like, the Z and the W minus and W plus. And then U1 is 1-dimensional, and the gauge boson is of course just a photon. And the fermions, they group up into multiplets. Group up into multiplets. That transform under the irreducible representations of this gauge group, or if you like, of the corresponding Lie algebra. So what is the corresponding Lie algebra? So if I have a product of groups, and the Lie algebra is going to be the direct sum of the Lie algebras of these. So of SU3, direct sum SU2, direct sum U of 1. Okay, so that is a standard model in a nutshell. So what is the hypothesis of grand unified theories? So it is based on the fact that if you look at the gauge couplings for the 3 different forces, they seem to, they run with the energy scale. But if you look at very high energies, these gauge couplings, they appear to converge, or to meet in a single point. Not quite, but fairly close. So on the basis of this, people have stipulated or hypothesized that perhaps this is not fundamentally the gauge group of particle physics. So fundamentally we do not have 3 distinguished forces. No, actually this gauge group is only a subgroup of a more fundamental gauge group. So the GUT hypothesis is the following. So it says that forces, the 3 forces, are unified into a single fundamental force at high energies, say energies way beyond what we can access with particle accelerators currently. Meaning that the fundamental gauge group corresponds now not to a direct sum of Lie algebras, but to just a single simple compact Lie algebra. So the fundamental gauge group corresponds to a simple compact Lie algebra G, and only at low energies this larger symmetry G is broken into the standard model gauge symmetry. That is spontaneously broken via some Higgs mechanism, via an analog of the Higgs mechanism, So the usual Higgs mechanism tells us how the SU2 times U1 electroweak force breaks into the individual electromagnetic and weak symmetries. Higgs mechanism to the subalgebra SU3 plus SU2 plus U1 sitting inside of this simple compact Lie algebra. So if we want to understand what are the options for the compact simple Lie algebras that may describe a more fundamental force in nature, we have to understand which of these compact simple Lie algebras can actually harbor a subalgebra of this form. And this is where the exercise above comes in, because here we've exactly seen how you can get a non-simple Lie algebra with a disconnected Dynkin diagram plus an additional abelian U1 component inside of a compact simple Lie algebra. So we have to find how the Dynkin diagram of this part. So what is this? So this is SU3, so the diagram is of this form. SU2, the Dynkin diagram is just a single node. So the direct sum of these has this rank 3 Dynkin diagram that is disconnected. So I want to find this inside the Dynkin diagram of the larger gauge group. So one thing we can already notice is that since this is a rank 3, we need at least a rank 4 Lie algebra to fit them in. And the simplest choice is the following, and this is called the Georgi-Glashow GUT. It takes this more fundamental gauge group to be SU5. So this one, so it, let's see, it can exactly fit this Dynkin diagram by dropping the node. So remember the SU5 Dynkin diagram is this one, so we're going to drop this node. Then exactly what is left is SU3 plus SU2 plus a U1 for the Proton generator corresponding to, not exactly this root, but the direction that is orthogonal to the other three roots. So this is really the simplest example, but you can look at more complicated examples. For instance, you could take also G to be SO10. So this is the next simplest example. So remember SO10, it has the Dynkin diagram as follows. So it's a rank 5 Lie algebra. People have also looked at G is E6. So this is the Lie algebra, this form. So this is an example of a grand unified theory based on one of these exceptional Lie algebras that we found in the classification of Lie algebras. And even people are looking at E7 and E8, or larger versions of the special unitary groups. Let's focus just a minute on this Georgi-Glashow grand unified theory, because it's really the simplest case. There we can really understand how, at the level of the Lie groups, these matrices fit into SU5. So at the level of the Lie groups. If we take a unitary matrix U in SU3, a unitary matrix U prime in SU2, and some phase e to the I phi in U1, then I can build a 5-dimensional special unitary matrix quite easily. I just put a U in the top left corner and a U prime in the bottom right corner. And then where can I put the phase? Well, I have to make sure that I can still multiply these U and U prime, but I want the determinant to stay equal to 1. So what I can do is I can write e to the let's say I phi over 3 here, and e to the minus I phi over 2 here. Right, because then taking the determinant of this matrix gives the determinant of U, which is equal to 1. Here I get, so 3, the third power of this, so that's e to the I phi, and here I get an e to the minus I phi, because this is a 2 by 2 matrix. So this is really in SU5. And you can check that this particular parameterization exactly corresponds to a procedure like this, where I drop the node in one place, assuming I've chosen the bases for my Proton subalgebra appropriately. Okay, so this is showing that really the standard model gauge group embeds nicely into SU5, and SU5 is really the smallest example in which I can do that. Now, of course, we have to do more, because okay, this takes care of the gauge bosons. We now know where they are. They have to be in the adjoint representation of SU5. But one still has to specify where all the fermions in the standard model go. And actually, this is one of the reasons that SU5 was quite popular at the time. We're talking about several decades ago. And the reason is that all the fermions in the standard model actually quite nicely fit into the irreducible representations of SU5. So let me just illustrate this by quoting a couple of these multiplets that appear. So I need to specify the multiplets of fermions. So they sit in the irreducible representations of SU5. So one of the irreducible representations of SU5 is just a fundamental representation. So it's a 5-dimensional one on which these matrices act. And for instance, what you can do there is you can put, so this is what Georgie and Glashow proposed, we can put the anti-down quarks in there, or down type quarks. So this is just for one family of the standard model particles. And then we can put in the leptons, so the left-handed electron and the left-handed neutrinos. So that gives 5 particles. And it makes so what is this 3? So these are the 3 different colors of the quarks. This makes sense because here we see that the 3 by 3 block at the top, that should be the SU3 symmetry, so that should act on the colors. So it's going to act on the colors of this anti-down quark. And then the other block, it should act on the SU2, so on the multiplets of the SU2 in the standard model. So these are really the lepton multiplets. Then there is also a 10-dimensional irreducible representation, which I did not derive for you, but it exists. And there one can fit exactly the 3 up quarks, the 3 up antiquarks, the 3 down quarks, and then there is just one left, and there we can put the anti-electron. So I don't have time to go into further detail, but there is really a nice grouping of the standard model particles in these irreducible representations of SU5. So they fit quite nicely. But okay, why is this model not so popular anymore? So it really has several problems. So let me mention just one problem. And this is the fact that, well, so this is a larger gauge group. So that means it has more gauge bosons. So here we had 8 plus 3 plus 1, so that's 12 gauge bosons. But SU5, that is 24-dimensional. So there are 12 extra gauge bosons in this SU5. And they are going to mix the quark and the leptons in non-trivial ways. So in particular, the extra gauge bosons their interactions lead to new lepton and baryon number violations. Lead to new lepton and baryon number violations, since they mix leptons and baryons. And one of the consequences of this is that you can calculate the proton decay rate, which for reasonable values of the coupling in this theory are actually in contradiction with experimental bound. So the proton decay is in contradiction with experimental bounds. So remember, I mean, the proton decay in as measured, the rate of the typical lifetime of a proton is actually measured to be longer than in the age of the universe. While for reasonable values of the couplings in this Georgi-Glashow GUT, they would predict a proton lifetime that is shorter than this. But there are various other difficulties as well. Now, of course, there are also possibilities to extend this by going to larger gauge groups. If you've got a larger gauge group, there is also some more freedom, more couplings in there that one can tune to get rid of these kinds of issues. There is also the issue that the couplings of the three fundamental forces in the standard model do not quite seem to converge at high energies, which may be solved perhaps by supersymmetry, but this is really going beyond the scope of this lecture. So I just wanted to present this to you as an application of the classification of compact simple Lie algebras. And I hope that with the material that I've presented in the past couple of weeks, that at least you will be well equipped to understand kind of more involved models of grand unified theories, or other models that go beyond the standard model. Okay, so thanks for your attention, and I wish you all good luck with the exam.